Introductory Statistics, Module 5, Probability. Section 5.1, Probability Rules. We'll look at these 5 objectives in this section. Probability is a measure of the likelihood of a random phenomenon or chance behavior. Probability describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. Now we will use the probability applet to simulate flipping a coin 100 times. Notice the plot of the proportion of heads against the number of flips, and then we'll repeat the simulation. So here's our probability applet, and we want to look here in the middle where we'll see a plot of the proportion of heads against the number of flips. So notice we have the flips set to 100, and we'll go ahead and click flip, and we see the simulation running. And we see that we got approximately 0.49 as the proportion of heads. So 49 out of 100 times heads was flipped instead of tails. So let's repeat this simulation. We'll reset it and then flip it again. And we see that we're pretty close. There were a couple more, but it was 0.51. Probability deals with experiments that yield random, short-term results or outcomes, yet reveal long-term predictability. The long-term proportion in which a certain outcome is observed is the probability of that outcome. The law of large numbers states that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. In probability, an experiment is any process that can be repeated in which the results are uncertain. The sample space, given by a capital S, of a probability experiment is the collection of all possible outcomes. An event is any collection of outcomes from a probability experiment. An event may consist of one outcome or more than one outcome. We will denote events with one outcome, sometimes called simple events, E sub I. In general, events are denoted using capital letters such as a capital E. In this example, we're going to identify events and the sample space of a probability experiment. Let's consider the probability experiment of having 2 children. Part A, we want to identify the outcomes of the probability experiment. So we see that we denote them with a little e. The first outcome is that we have 2 boys, a boy and then a boy. The second outcome is that we have a boy and then a girl. The third outcome is that we have a girl first and then a boy. And the fourth outcome is that we have a girl and then a girl. For part B, we want to determine the sample space then. Remember that the sample space is the collection of all of the possible outcomes. So we have our outcomes listed in part A, and we want to now list them together. So we list them as a group within brackets. And we see we have all 4 outcomes listed here. For part C, we want to define the event E as being equal to having 1 boy. So then that event would be defined as having these 2 outcomes, a boy then a girl, or a girl and then a boy. For Objective 1, we want to apply rules of probabilities. So let's look at some rules of probabilities. Number 1, the probability of any event E, given by P parentheses E, must be greater than or equal to 0 and less than or equal to 1. So in order to write that mathematically, we simply put P parentheses E in a double inequality with 0 and 1 on either side, knowing that it can also be equal to those 2 values. So that's why we have the bar underneath our inequality symbol. Number 2, The sum of the probabilities of all outcomes must equal 1. That is, if the sample space, given by S, is equal to these given outcomes, E1 through En, then the probability of those will sum to 1. A probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy rules 1 and 2 of the rules of probabilities. So let's look at an example of a probability model. In a bag of peanut M&M milk chocolate candies, the colors of the candies can be brown, yellow, red, blue, orange, or green. Suppose that a candy is randomly selected from a bag. The table shows each color and the probability of drawing that color. We want to verify that this is a probability model. So in order to be a probability model, it must satisfy both of our rules of probabilities. So first we look and see that all of the values are numbers between 0 and 1 inclusive. So it does satisfy rule number 1. The second rule was that the sum of them must be equal to 1. So we see when we add them together that we do get 1, and therefore rule 2 is also satisfied. So this is a probability model. If an event is impossible, the probability of the event is 0. If an event is a certainty, the probability of the event is 1. An unusual event is an event that has a low probability of occurring. Objective 2, we want to compute and interpret probabilities using the empirical method. Approximating probabilities using the empirical approach. The probability of an event E is approximately the number of times event E is observed divided by the number of repetitions of the experiment. The probability of our event E is approximately the relative frequency of E, which is then equal to our frequency of E divided by the number of trials of our experiment. So let's look at an example where we will build a probability model. Pass the Pigs is a Milton Bradley game in which pigs are used as dice. Points are earned based on the way the pig lands. There are 6 possible outcomes when one pig is tossed. A class of 52 students rolled pigs 3,939 times. The number of times each outcome occurred is recorded in the table at the right. So we see we have 6 outcomes: a side with no dot, a side with a dot, a razorback, a trotter, a snouter, and a leaning jowler. So for part A, we want to use the results of the experiment to build a probability model for the way the pig lands. So remember that this is going to be just like we did in Module 2 where we were calculating relative frequencies. So remember the total number of times that the children rolled the pigs was 3,939. So to get our relative frequency, we will take each frequency amount given in our table up above and divide it by our total. So for the side with no dot, we have 1,344, which we want to divide by our 3,939. And we get approximately 0.341 for that probability. And we continue so on. And this is now our probability model for the way the pigs land. In Part B, we want to estimate the probability that a thrown pig lands on the side with a dot. We can see in our table that the probability a throw results in a side with a dot is 0.329. That means that in 1,000 throws of the pig, we would expect about 329 to land on a side with a dot. In Part C, would it be unusual to throw a leaning jowler? So looking at the table, we see that the probability of throwing a leaning jowler would be 0.008. So this would be unusual, since we would expect that in 1,000 throws of the pig, we would only obtain a leaning jowler about 8 times. Objective 3. We want to compute and interpret probabilities using the classical method. The classical method of computing probabilities requires equally likely outcomes. An experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. So computing a probability using the classical method, if an experiment has n equally likely outcomes, and if the number of ways that an event E can occur is given by m, then the probability of our event E, P of E, is given by this formula. It's the number of ways that E can occur, which was m, divided by the number of possible outcomes, n. So if S is the sample space of this experiment, then we have this formula here, where n of E is the number of outcomes in E, and n of S is the number of outcomes in the sample space. So let's look at an example where we will compute probabilities using the classical method. Suppose a fun-sized bag of M&Ms contains 9 brown candies, 6 yellow candies, 7 red candies, 4 orange candies, 2 blue candies, and 2 green candies. Suppose that a candy is randomly selected. What is the probability that it is yellow? So the probability of getting yellow would be equal then to the number of times we can get a yellow divided by our total number of outcomes in the sample space. So the number of times we can get yellow would be 6 out of our total, where we want to add up all of the candies. So we have 9 plus 6 plus 7 plus 4 plus 2 plus 2. So we see that those total to 30, so we have 6 out of 30, which will give us 0.2 as our probability that it's yellow. Now let's look at what the probability is that it's blue. So the probability of getting blue would be equal to the number of blue candies divided by the total number of values in our sample space. The number of blue candies was 2, and remember from before that a total number of candies in our sample space was 30, which is approximately 0.067. So let's comment on the likelihood of the candy being yellow versus blue. So the probability of getting a yellow was 6 out of 30, and the probability of getting a blue was 2 out of 30. So we see then that selecting a yellow is 3 times as likely as selecting a blue. Objective 4. We want to use simulation to obtain data based on probabilities. Let's look at an example using a simulation. We want to use the probability applet to simulate throwing a 6-sided die 100 times. We will then approximate the probability of rolling a 6 and compare this to the classical probability. We'll then repeat the exercise for 1,000 throws of the die. So first let's look at the classical probability. The probability of rolling a 6 would be the number of times that we can roll a 6 out of the total number in the sample space. So remember, in a 6-sided die, one side is a 6 out of all 6 sides, which is equal to about 0.167. Now let's look at our probability applet. So first we're going to roll the die 100 times. And we see that rolling the die 100 times, we get about 0.1. So it's a little bit less. Now let's reset it and change it to roll it 1,000 times. You can see as it's going that our classical probability value that we already calculated is the green value in the middle, and that the line is very close to it the higher we get. So rolling our 6 out of 1,000 times, we got about 0.169, which was really close to the classical probability. So we've demonstrated now the law of large numbers. The more times we roll it, the closer we get to the actual probability. Objective 5. We want to recognize and interpret subjective probabilities. The subjective probability of an outcome is a probability obtained on the basis of personal judgment. For example, an economist predicting there is a 20% chance of a recession next year would be a subjective probability. So let's look at an example. In his fall 1998 article in Chance magazine, a statistician reads the sports pages. Hal Stern investigated the probabilities that a particular horse will win a race. He reports that these probabilities are based on the amount of money bet on each horse. When a probability is given that a particular horse will win a race, is this empirical, classical, or subjective probability? This would be subjective because it is based upon people's feelings about which horse will win the race. The probability is not based on a probability experiment or counting equally likely outcomes.